In this video, we'll be discussing how calculus is used in economic analysis. Economics explores the choices that humans make in regard to the production, distribution, and consumption of resources. While the world has a limited number of these resources, the desire for them can be infinite. And this leads to the need for people to make choices about how to use the resources that have been given to them. The economic industry analyzes the best possible solutions to these problems. Economics can be broken down into two major disciplines, microeconomics and macroeconomics. Microeconomics refers to the behavior of the individual person or group within a larger economy. This could be a person, a firm, a business, or an industry. Macroeconomics studies the entirety of the global economy. Some of the economic factors that macroeconomics analyzes include GDP and GNP, prices of goods, or inflation rates. So, a number of problems that economists face can be solved quantitatively, and they often require the use of calculus. Sometimes the problems are producer and consumer surplus problems, and this is pretty much the relationship between what a producer wants and what a producer is getting for selling a product, or what a consumer wants to pay compared to what the consumer is paying for a product. But more than likely we have optimization problems. And optimization problems find the derivative of a function in order to make the smartest decision about a product. This is done through finding the maximum or the minimum values. These values are most often used when analyzing cost, profit, price, and demand. For example, a function can be used to minimize cost of a unit or to maximize the profit. And most often these functions are univariate, meaning they only have a single variable which must be maximized or minimized in order to find the best solution. However, this is not always the case, and in quite a few functions it would require multivariable equations. For example, the total profit of selling one unit of a product could be dependent on both the cost of producing it and the revenue from selling it. A number of complex economic functions have been created using multivariate equations, such as the Hicksian or Marshallian demand functions. To solve these problems, a basic understanding of partial derivatives is needed, and in simple terms, a partial derivative is the derivative of a multivariable function, for example f, x, y, in regard to only one of the variables in the equation. For this to work, the other variable will be treated as a constant and regular calculus rules would be applied to it. The second direct partial derivative, so when I say that, the second direct, so that's the second derivative, and the direct would be, if you're taking the derivative of x, it would be fxx, or if you're taking it of y, fyy. So the second direct partial derivative can also be found using the same rule to determine if the critical points are maximums or minimums. A cross-partial derivative involves finding the first derivative of one of the variables, and then finding the second derivative in regard to the other variable. And for most multivariate functions, there are three conditions that need to be met in order for it to be optimized. So the first condition is that all first order partial derivatives must equal 0 when evaluated at the same point. So this is just saying that the derivative of a function is equal to 0 when you have a stationary point, so it's just like a normal function. Secondly, it is required that both second order direct partial derivatives, so second order, second derivatives, direct fxx or fyy, have the same sign when evaluated at the same point. So this guarantees that the maximum or minimum will be found, and is crucial to avoid shapes of functions such as saddle points, where one of the second direct partial derivatives is a maximum and the other is a minimum. Lastly, in order to make sure that the critical points are not points of inflection, the function must meet the requirement for fxx times fyy is greater than fxy to the power of 2, which is basically just a point of inflection. A lot of univariate and multivariate problems, they can be unconstrained, but it's far more realistic for them to be constrained. And in an economic problem, this could be like the overall profit for selling a product is limited by the budget you have for producing a certain unit of that product. And these problems can be solved using Lagrange multipliers, which I will talk about when we get to it. Alright, so the first problem is this. Suppose that the total cost function for a manufacturer is given by total cost is equal to 4x cubed minus 72x squared plus $510x. And asks us to determine the level of production that minimizes the average cost. So the level of production, or the quantity of units, or the number of things that we're selling, is x in this question. And asks us to find average cost. And to find average cost, all we have to do is divide the total cost by x, the quantity of units. And so for this equation, we would get 4x squared minus 72x plus 510. Alright, so that is our average cost formula. And now, like all optimization problems, for the average cost, we're going to find the derivative in order to figure out the stationary points. So the derivative of this function, 8x minus 72. And we're going to make it equal to 0. And now we just solve for x. So plus 72 on both sides, whoops. And then we'll divide by 8. And we'll eventually get x is going to be equal to 9. So x is equal to 9 units. And now, to determine whether this is a minimum or a maximum or a stationary point, we don't quite know yet, we have to do a second derivative test. So we'll do that. The actual cost, the average cost, find the second derivative, and then this is the average cost of first derivative, and so it's pretty simple. We can see from here that it's just going to be 8, which is greater than 0, and therefore we have a minimum. So we've solved that problem. We've found the minimum value, which is going to be x equals 9, that will have the lowest total cost for our function. Okay, so our second problem is quite a little bit more difficult because it has two variables in the equation. And here's the problem. A company's function for total cost depends on both the quantity of units sold, x, and the laborers required to produce the product, y. For the function, z is equal to 7x squared minus 80x minus 2xy minus 4y plus y squared plus 19. Find the optimal level of x and y that minimize the total cost. So as I was saying before, what we do with equations like this is we find the partial derivatives in terms of both variables. So we're going to find the partial derivative of z in regards to x here. And what we do, once again, we treat y as a constant. So the start will stay the same, 14x minus 80. And here, y is a constant and negative 2 is a constant, and x is being multiplied by both of them. So if you have a constant multiplied by a variable x, you just get rid of the variable and have the constant remain. So we'll have negative 2y. And the rest of the equation we will just get rid of because it's all constants and they disappear when you find the derivative of a function. Now we'll just do this exact same thing for y. Negative 2x minus 4 plus 2y. Alright, so we have both of our equations now in the partial derivatives of the function in regards to x and the first partial derivative of the function in regards to y. So now what we do, set them both to 0 and solve a set of simultaneous equations. So let's just solve for y in this first one. So I'm going to add everything to the other side except the negative 2y. And so we're going to have negative 2y, it's going to equal to negative 14x plus 80. And divide everything by negative 2. So that we'll have y is going to be equal to 7x minus 40. Alright, so now we have a formula for y. We can plug this into the y here in the second formula. So let's do that. So negative 2x minus 4 plus 2 times 7x minus 40. Sorry for being a little scrunch up there. And now we just solve for x here. And it's going to equal 0. So we're going to have, let me just draw a line here. So we're going to have negative 2x minus 4 plus 2 times 7x, 14x, 2 times negative 40, 80, equals 0. Now we'll put everything, we're going to put the constants on the other side and combine the x's, and we'll end up with 12x is going to be equal to 84, and therefore x is going to be equal to 7. Perfect. So we have x equals to 7. Now we can solve for y by plugging it into this original y formula that we had here. So 7 times 7 minus 40, which is 49 minus 40, which is going to be 9. So we have x equals 7 and y equals 9. And that fulfills the first criteria that we have, that we set both of them, the equations, equal to 0. Now the second criteria, once again, is that there's second derivatives. So z, second direct partial derivative of x, which is just this, and doing it once again in regards to x. So negative 2y will disappear because it's constant, negative 80 will disappear, 14x will just become 14. And the second direct partial derivative in regards to y, everything will disappear except the 2y, and the y will detach itself from the 2, and we'll just have 2. And as we can see here, both of these are greater than 0, and so we just need to fulfill the third requirement now to conclude that they are a minimum. This is a minimum critical point. And the third requirement, as you may have remembered, is that we need to check that it's not a point of inflection. And to check that it's not a point of inflection, we need to find the partial, the second cross partial derivative. So z in regards to x for the first derivative, and then in regards to y for the second derivative. So we already have the formula for z in regards to x for the first derivative here, and now we just do this, but in regards to y. And as we can see, like we've been doing just before, it's just going to be negative 2. So this is negative 2. And now it needs to fulfill the formula to make sure that this is a minimum and not a point of inflection. Sorry. It needs to fulfill zxx times zyy is greater than zxy squared, which is going to say 14 times 2 is greater than negative 2 squared, which is obviously true because we have 28 is greater than 4. Right, so now we have fulfilled all three criteria, and we can safely say that having the units sold as 7 and the number of laborers required as 9 will minimize the total cost of selling our product. Okay, so our third and final problem is going to be constrained optimization problem. And so here it is. The budget for a startup company in regard to the cost of producing a unit X and the cost of materials purchased Y is X plus Y is equal to $270. For the cost function, Z equals X squared minus 2XY plus 6Y squared. Calculate the values of X and Y which will minimize the cost. Alright, so we have our equation and we have our constraint. And as I said before, we're going to use a thing called the Lagrangian multipliers. And what this does is we're going to multiply our constraint by a proportionality constant. In this case, it's going to be lambda, which is just another Greek alphabet letter. And that is going to make it proportional to our equation. And then we'll be able to subtract it from our equation to create the Lagrangian. So the Lagrangian is going to be equal to our equation, 2 6y squared minus our Lagrange multiplier, lambda, times by our constraint. But before we can do that, we have to, now that we have a lambda, it's a new constant, a new variable in fact, sorry, we have to make it equal to 0 because that is to meet the first condition of multivariate functions. We have to have, at the same point, all variables equal to 0. And so, to do this, we'll just minus 270 off from this function and create 0, and then multiply it by lambda. Alright, so we have lambda multiplied by x plus y minus 270, and then it's going to equal to 0. So this is our Lagrangian. And now that we have our formula out of the way, this is the easy part now. We're going to find the partial derivative of all three of our variables, x, y, and now lambda. And then from there, we will be able to solve for x and y. So, partial derivative looks like this. Partial derivative of L in regards to x is just going to be 2x minus 2y minus lambda. So we keep lambda in here because if we think about this, lambda is just a constant multiplied by x plus y minus 270, which could be anything, could be like a, and so we just leave the constant there. And so for y, it's just going to be negative 2x plus 12y, treating the other variable as a constant, as always, and minus lambda. I'm going to make them both equal to 0. And there we go. We have our partial derivatives in regards to x and our partial derivatives in regards to y. Alright, so now we just need to do our partial derivative in regard to lambda. And all this is just our original constraint function. X plus y equals 270. For the same reason that I just mentioned before, it works like this. Alright, now we need to do simultaneous equations to both these functions. And as you can see, we can just add lambda from the left-hand side to the right-hand side on both equations. So they're both equal to lambda. So we will have 2x minus 2y is going to equal to lambda, which is going to equal negative 2x plus 12y. And in this situation, lambda is just going to be equal to 0. Alright, so now we will just get all the variables on one side. So plus 2x on here, so we have 4x. And why did I put 2y here? Sorry, 12y. Minus 12y here, so we have minus 14y going to be equal to 0. And now, if we plus 14y on both sides and then divide by 4, we'll find that x is going to be equal to 3.5y. And this isn't definitive yet, but we can now plug 3.5y in to our constraint here, because we know that x is 3.5 times y, so we can plug that into constraint and then find what y is in regards to our constraint. So let's just do that. So 3.5 for y plus y is equal to 270, or 4.5y is equal to 270. And when we divide by 4.5, it comes out that y is going to be equal to 60. Right, so now we know y is equal to 60. Perfect. And now we can just plug that into our x equals 3.5y. So x equals 3.5 times 60, which is going to be equal to 210. Now obviously from here, we would just get the second derivatives and make sure that it's a minimum instead of a maximum or a point of inflection, and then we could solve the problem from here. But what we have actually done is we have had the constraint of $270, and we have found the optimal way, in this case, spending $210 on producing the units and $60 on purchasing the materials in order to decrease our cost, have the lowest cost. So that was a very quick overview of the problems that calculus can solve in the economic industry. If I had more time, I would have gone into further detail, but as you could probably see, I already went way over time, but I don't think I went into enough detail. The problems were probably a little confusing, but I've already gone way over time. So I hope this video just gives a basic rundown of how calculus can be used in economics.